Continue. When light is emitted from a point source, so like this is the point of disturbance, and it will form a concentric circles. So what we can understand in this situation is, when light is emitted from a point source or a wave is emitted from a point source, then the structure of the wavefronts is concentric circles. Concentric circles means has the common center with different radii, many circles are formed, with this common center too is normal to the all localized planes. If you understand the concept of equipotential surfaces, along a charge, around a charge there is a potential surface formed. In each curve the potential is common, a potential is same. So in this curve, if you want to find out the potential difference is 0, because each curve is treated as an equipotential surface. The same concept we are applying here. This is the point of disturbance. Wave is means the source of the generated wave is a point source. Then the wavefronts will appear as a concentric circles, where the center is common to all and normal to all. So like this. Next one, if a source is a line wave or a lengthy one, how the wavefronts will be appeared. Next, if the source is line source, if it is a line source, then this is the line source. With respect to this, means along this line source, the light is emitted or waves are emitted. Then the wavefronts will be coaxial cylinders. So like this, coaxial cylinders, where the line source is tangential to every cylindrical surface, which is similar to the line charge distribution with respect to the coaxial cylinders in Gauss law. So if line source, the wavefronts are coaxial cylinders. The third one, when a light source is emitting the parallel rays, or light is coming from the far off sources. When a source is emitting parallel rays, or light is coming from a pair of sources. In this case, the wavefronts will be like this. These are the parallel light rays. Then what we can understand about the wavefronts, these wavefronts will be like this. So we can say it as a a parallel wavefront, a parallel guided wavefront. So when a source is emitting a parallel light rays, or light is coming from a pair of sources, means seems to be parallel to each other, then we can expect a parallelly guided wave front in this case. As the light rays are parallel to each other, the wavefront which is formed by these light rays is called as plane wavefront or planar wavefront. We can say it as a plane wavefront or planar wavefront. This is the important one, we can say. So like this, which is localized in a plane. So that's why we can say this is the planar wave front. Next concept is secondary wavelength. So what is secondary wavefront? Up to now we have discussed about the primary wavefront, the first wave, the line which is near to the center. So what is secondary wavefront? Let us suppose if this is the source of the disturbance and I am drawing an imaginary surface at any given instant of the medium. This imaginary surface which is drawn around the point of disturbance with respect to given source is called wavefront. We know this. Each point on this wavefront, each point, we can take any point in this wavefront has some velocity. Each point of this wavefront is a fresh source which can create the disturbance to the next level. Each point on the primary wavefront acts as a fresh source of disturbance to the next level. For the next level. That means the point in this primary wavefront creates the disturbance, and this disturbance will shift to the next level. Because of that, one more circular waveform is forming. And the point of this one creates another disturbance or acts as a fresh source to create the next level disturbance. These are called secondary wave fronts, and these secondary wave fronts can travel in all directions with the speed of light. These secondary wave fronts can travel in all directions with the speed of light. With speed of light or with a speed of light to all directions, not only localized to one plane. It can travel to all directions. So whenever these waves are traveling, one surface or a river bank, these wave fronts which touches the river bank. So any plane or any point or any surface which touches the secondary wave fronts Actually it is tangentially forward actually, which gives the shape and structure of the wavefront. Means when it touches, these waves will be reflected back to the original position, and it will create a circularly polarized waves like this. So circularly polarized waves, we can draw it as a circular. That means this is the particle, first primary, create the disturbance to the next level, create the disturbance to the next level. Like this it will be continued, and a plane which touches the secondary wavefronts, which gives the shape of the secondary wavefronts. Now we will see the clear picture of the secondary wavefronts and its structure. Now what is the shape of the secondary wavefronts? Like this. B, A, around it B dash, A dash, this is BA, this is B dash, A dash, and this is B double dash, A double dash. So what is the shape of this circular wavefront? Circular, because it is touching the surface here. We can draw an imaginary line like a river bank. Then the wave is circularly polarized with velocity c. C is nothing but velocity of light. But what is the distance of these circularly polarized waves or circular wavefronts, which are called as secondary wavefronts? C delta t. Because distance traveled by these wavefronts, C is equal to dx by dt, we can write dx is equal to C into delta t. One more circular. One more circular, one more circular, one more circular, like this. So each one's distance is C delta t. So like this is the shape of secondary wave fronts within a given wavelet.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.